Hi Year 10, today we're still looking at statistics. However, we have moved on from reviewing statistics and we're looking at bivariate data, which is exercise 902. So statistics that we have seen before have involved analysing data for a single variable, such as measuring heights, counting types of vehicles. Sometimes data may be obtained about two different variables that may or may not be related, such as measuring the arm span and the height of a group of people, or the English and math marks for a class of students. This is called bivariate data. And we often want to analyse this data to see if there is a relationship that exists between the two variables. So in some cases, one of the variables is time, and we measure another variable against it to determine if any pattern exists. For example, we could measure the height of a young child each month. In this case, the dependent variable is height in centimetres because each measurement depends upon the month in which it was taken, and the dependent variable is the age in months. This table shows the average height of a particular young child from 18 months to 24 months. We can notice that the height is increasing each month. For this 6-month period, the child has grown 4.1 centimetres. This is an average increase of approximately 0.7 centimetres per month. We can draw conclusions from any observed pattern in bivariate data, but we need to take care not to make assumptions that cannot be supported. For example, if we were to assume from this data that the child will grow 0.7 centimetres in height every month, assuming this is true, what would the height of the child be at age 7? So at age 7, what we have is the child's height at the end of 2 years. So what we know is that the child's height at 2 years equals 80.2 centimetres. So at 7 years, it will be equal to 80.2 centimetres, plus we now need to go 7 minus 2 years, which is 5 years. So it'll be 5 times however many months there are in a year, which is 12, times how the average centimetres that will grow, which is 0.7. So when we put this into our calculator, we get that the child would be 122.2 centimetres tall. So this is reasonable. It could be true. Now let's try for a 16-year-old. So that's like your age, right? So at 2 years old, the child is 80.2 plus. Now we need to go 16 minus 2, which is 14, times the number of months in a year, which is 12, times our 0.7, which is the average that the child is growing each year. So we go 80.2 plus 14 times 12 times 0.7. And we get that the child is 197.8 centimetres tall. So this, a 16-year-old is approximately 2 metres tall here. So does these heights seem reasonable? So to extend the data beyond the data that has actually been measured is to extrapolate the data. So it is obvious that an incorrect assumption has been made, as we cannot expect the growth rate to be constant throughout the child's life. In other examples, incorrect assumptions may not be so obvious, so we need to ensure that any conclusions we draw or you draw can be supported by the data. Let's have a look at an example. So this table shows two sets of data measured against the time of the year. For each month, the highest temperature in degrees Celsius for the 30-year period between 1981 and 2010, and the single year of 2011 was recorded at Observatory Hill in Sydney. What we want to do for part A is graph these sets of data on the same diagram and join the plotted points to form continuous line graphs. Does the line joining adjacent points have meaning? So what we have here is we are going to plot our points of our maximum temperature in blue, and we will plot our points of our maximum temperature in 2011 in green. So I'm going to just zoom in a little bit onto this graph. I still have the table in front of me. So what we want to do, our first point is in January, the maximum temperature in of 1981 to 2010 was 44.2. So we're going to put a dot where this is. So in January, we want to go to 44.2. So we'll put a dot there. Then for February, it is 40.8. So 40.8. Then we have March is 39.8. Then we have April is 33.9. It's about there. Oh, hang on, it's about there actually, because it's nearly 34. Then May is 29.0, which is there. Then we have June is 25.2. July, we have 25.9, so a little bit higher. August is 31.3. We have September is 34.5. We have October is 38.2. November is 41.8. And December is 40.9. So now what we want to do is we want to join these dots using a straight line. I'm just going to make the dots a little bit more prominent. And we want to join the dots using straight lines. So we're doing like a connect, like a dot to dot, really. Like so. Now we want to do the exact same for the maximum temperature in 2011, which we're doing in green. So in January in 2011, it's 35.4. So 35.4. Then in February, we have 41.5. Oops, which is about there. Hang on. I just need to zoom in. There we go. Then in March is 33.6. In April, we have 27. In May, we have 23.3. Oh, that's more like, yep, there. Then in June, it's 21. July, we have 21.4. August, we have 25.7. September, we have 32.5. October, we have 34.3. November, we have 37.2. And December, we have 26.8. Which is roughly there. So now we want to do the exact same thing and we want to connect these dots. Oops. We want to connect these dots using a straight line. So we want to make sure that we are using a ruler here. It is very important. Like so. Awesome. So what we have done is we have graphed these sets of data on the same diagram, joined the plotted points to form continuous line graphs. Now we have a little end part of our question where it says, does the line joining adjacent points have meaning? So the graph has been constructed within months on the horizontal axis and temperature on the vertical axis that has been truncated from 0 to 20. So that means that we have our two lines here. That means that we don't have the numbers from 0 to 20 included. And this is because there is no data in the range between 0 and 20. So time is usually shown on the horizontal axis whenever we are looking at bivariate data, and plots along the line segments cannot be read as data points, but the line does indicate a trend between the data points. So the lines joining, to answer this question, adjoining adjacent points are not read as data points, but they indicate a trend. Okay, we now have part B. So part B says, for which months was a maximum temperature recorded in 2011 that was higher than for the previous 30 years? So if we have a look back here, the only data point that is, which our green line is when we're talking about 2011, that's higher than our blue point, which is our maximum temperature recorded, or our temperature recorded between 1981 and 2011, is this green point here. And the exact data, so that's in February, so we're talking about this point here, so it's in February in 2011 with a temperature of 41.5. So Feb had the highest temp of 41.5. Then part C says, what feature is unusual for 2011 compared to the previous 30 years? So for 2011, the thing that's the most unusual is, in fact, the biggest difference is this drop in December. So that drop in December, which is normally our summer months, seemed very low. So the maximum temp in December is our answer there. Okay, moving on to example 2. So we have the New South Wales Centre for Road Safety published these figures for car driver deaths in 2010, showing the age and sex of the driver. So what we want to do is we want to draw a column graph showing both male and female data on the same graph. So we have our graph set up here and we want to draw our columns. So for our male data, I'm going to do blue columns, and for our female data, I will do red columns. So for our males aged 17 to 20, it is 16. So we want to do a column for 16. So we need red because we're talking about males, and so we're going to go up to 16, like so, like so. We might have to turn that off. And we draw a straight line. So you want to use a ruler here, and you can choose to colour them in. I'm not going to, as it will take a lot of time. And then females, we have that they are 10. Then for ages 21 to 25, we have males is 17. And then we have females is 4. So this is very time consuming, but it's important that we do it right and with a ruler. So 26 to 29 for males is 5. And for females, it is 0. So when something's 0, we just do a line along the axis to indicate that. So then for 30 to 39, for males, it is 13. Oops, that was meant to be a straight line. And for females, it is 5. For 40 to 49, for males, it is 14. And for females, it is 2. for 50 to 59 males is 13. Oh, we've gone too far. And for females, for 50 to 59 is 6. Then for males, 60 to 69 is 9. And females is 5. So we can start to see a bit of a trend here occurring. And then for greater than 70, we have that males is 16. And females is 9. Oh. So males is 16. Females is 9. Like so. Okay, so there is our column graph showing our data. And it's important that we have these little gaps in between our data as well. So then for part B, it says, why is a line graph not suitable for this data? So a line graph is not suitable for this data as the horizontal axis is categories. So because the horizontal axis is categories, we use a column graph. So then which group appears to be the safest drivers? So for the 2010, the group with the safest driving record appears to be the female drivers, aged 26 to 29, as they have 0 occurring there. And the group that appears to be at the most risk, when we look at it, we would think it would be males aged 21 to 25. However, it's important to note that the greater than or equal to 70 represents more than 10 years. It should be noted that this category the 21 to 25 only represents 5 years, whereas the 17 to 20, males aged 17 to 20, represents 4 years. So it has a worse average. So 5 years, 17 deaths. However, males aged 17 to 20 has 4 years, 16 deaths, therefore higher average. So our answer there is the males aged 17 to 20. So then part E says, has the data been organised to give a fair picture of the driving risk of various ages? So the data is distorted because we do not have equal spreads. So what I was saying before is that our 17 to 20 is only 4 years, our 21 to 25 is 5, but our greater than 70 is more than 10 years. So the data are not in groups of equal spread. So therefore it's not fair. Picture. Because it's distorted. So how would the data be used? So if you think about where somebody would use this sort of data, so they would use it in insurance companies. And insurance companies would use this data and rely on this data when assessing the risk and therefore setting the premiums for their insurance. And yeah, that's one of the ideas. So then part D has the number of drivers in each age category being given. So no, we don't know how many how many males there are between the ages of 17 to 20 out driving, or how many people over the age of 70 are out driving. So we can't get a percentage idea of who's the worst driver.